we're going to do now is we're going to change something in the same circuit that we just went over in the last video. And that is going to be, we're going to change the frequency, and we're going to see what type of effect that has. So we're going to come in here, and we are going to change the frequency to 25 hertz. Okay? Let's make some predictions before we get started. All right? If I take the frequency down, my X of L is going to get lower. Okay? If my X of L gets lower, okay, then my current is going to go up, because if my X of L goes lower, my impedance is going to get lower. That's going to increase my current. Okay? That's one prediction. All right, another prediction we can make is that if my X of L gets lower, my phase angle will get lower as well. Because if my X of L is lower, and my R, of course, is going to stay the same, okay, my phase angle will shift. Okay, so let's see if those predictions come true. And make another prediction if we wanted to. I'll get more voltage drop across my resistor, all right, than I did in my previous one, and the voltage drop across my inductor will be less. And then that would relate over to power as well. So let's take a look at these circuits and see if these predictions come true or not. Okay, there's no new math here. Okay, all right, there's no new formulas or anything like that. We're just going to walk through and see what happens when the frequency changes. Okay, and this would have a similar effect, the exact effect actually, if we put a smaller inductor in there. Okay, so let's go ahead and start off by calculating out our X of L. Okay, and again, I'm not going to run through all the formulas. You still have your formula sheet right here. Okay, all right, you guys still have that. You have all that written down. So we're going to go 2 pi times 25 times 0.33. Okay, sorry, my stylist, again, it's not the greatest. So we'll do 2 times pi times 25 times 0.33. And that equals 51.8. And you know what? I think we're going to just go ahead and round that up to 52 here. Okay? 52 ohms. Okay? My resistance down here is 68. Now, if I were to graph this out, so again, let's make each of this 100. Okay? I would be right in the middle here, and I would be a little bit past the middle right here. All right? So when I graph this out to show my Z, I'm going to be less than 45 degrees, which is what we predicted, because we're now more resistive. And we're more resistive, why? Well, because this is 52 ohms and this is 68 ohms. Okay? And so we're going to be below that 45-degree phase angle mark. All right? So now let's go ahead and calculate out Z. All right? And that is going to be the square root of 52 squared plus 68 squared. Let's go ahead and put this into my calculator here. 52 squared plus 68 squared equals, come over here, take the square root. I'm at 85 now. 80, oh boy, drawing 8s on this thing's a nightmare. 85.6. Okay? 85.6. Now, the next thing is going to be to calculate out the phase angle. Okay? And my phase angle is the inverse, inverse tangent of x of L over R, okay? And so this would be, go ahead and erase this actually real quick. This is going to be 52 over 68. Okay? So 52 divided by 68 equals, take my inverse tangent, I am at 37.4 degrees. Okay, so I'm at 37.4 degrees. That's really good. All right, very cool. So now what do we see here? Let's walk through what happened from our last one. My frequency went down for some reason. My X of L went down. Okay, all right. My X of L is lower. Okay, more than, pretty significantly, more than half. Okay, my R has stayed the same. My Z has gone down. Okay, and now my phase angle has gone down. The next thing we need to do is calculate out that I total, which we predicted should go up, right? So it'll be 120 divided by 85.6. Let's go ahead and type this in. So we got 120 divided by 85.6. And my IT equals 1.4 amps compared to the 0.184 that it was before. Okay? So now I know my current has gone up. Now just think about that. All I did was change my frequency. The only thing that happened was my frequency dropped. And this would be the same thing, guys, is if our impedance went, if our X of L went down. Okay? So if my inductor went down. Okay, so now that we know our current total, okay, make this a little bit smaller, X of L, so it'd be times 1.4, okay? Now I can use these to begin to get all of my other formulas. So I'm going to go ahead and erase this, so snap a picture of it if you need it before I do that, okay? All right, so now let's start to get my voltages. So I'm going to do voltage L is going to be my X of L times IT, which is going to be, it's going to be 52 times 1.4. So let's go ahead, and I have my 1.4 up here already, so I'll multiply that by 52. And my voltage drop is going to be 72.9 volts. Okay, that couldn't be written much uglier. 79.2 volts. Okay, let's compare that before. We had 104, right? So we now have less voltage drop across there. Where's that voltage going to go? My prediction is, and I think your prediction as well, is going to be it's going to drop across the resistor. So let's figure that out. Okay, so this is going to be 68 times 1.4. So let's go ahead and clear this out. 1.4 times 68, and that equals 95.2 volts. Okay? All right, again, that's pretty ugly. Let me switch that up. Okay. And again, I know you guys are getting the points of this, but still, professional standards and all. All right. Now, we know what our voltage total is. It's 120. And I can prove that through Pythagorean's theorem. So if I take 79.2 squared plus 95.2 squared, and I inverse that, I'm at 95. Oops, I think I typed that in wrong. Okay, let's try this again. Ah, I see. One of the things is this is supposed to be 72.9. Oh no, a mistake. How does that happen? So this is supposed to be 72.9 volts. Okay, all right, my dyslexia just kicked in there, and my students weren't there to correct me. All right, squared plus 92.5 squared equals, take the square root of that, and I'm at 117.7. Okay, so you can tell that the way that I rounded here or something back here affected a little bit, but that is well within my my range. Okay, to be 2.3 volts off out of 120, perfect, totally nailed it. So we're good there. Okay, now let's figure out our phase angle. Okay, so here's my phase angle. That's going to be inverse tangent over my VT, which is 72.9 over 95.2. Did I do that again? Maybe that's why my value is off. Let's go ahead and try this. Okay, let's go ahead and see what happens here with my which one I wrote down, because it looks like here I got this mixed up as well, which might account for the little bit of a difference that I had in my voltage drop. Okay, so I'm doing this to make sure you guys are paying attention, screaming, "He wrote down the wrong number!" Okay, so let's go ahead and do that. We're going to do 72.9 divided by 95.2 equals inverse tangent 37.4. Look at that. Okay, I'm going to run my Pythagorean's theorem one more time with the right values in here. It'll only take a second to get my voltage total and see if that's why I was off. All right. That's why these quick mental checks, look at that. 119.9. Now we're 1.1 off. Okay. My first one, when I wrote it down wrong, bad. This, good. Okay. This is very, very cool. And so now I know I'm dead on. And this is why these quick mental checks are right. Let's say I had kept this at, I had kept this switched, my phase angle would have been off. Bear in mind, I'm only 3 volts off when I switch those, but I make mistakes like this all the time. All the time I make mistakes like this. That's why I'm always doing those quick mental checks. Okay? So the next thing I'm going to do is I'm going to start to work on my power. So I'm going to multiply, make this a little bit smaller. I'm going to multiply this by 1.4 the same way that I did before. So I'm going to snap a picture of this before I delete it if you need it. I really like this type of electronic mathematical calculations because it's so easy to keep verifying your work. I just really appreciate that about this. You know, I make so many typing mistakes, and as you can see, just switching numbers around, that I really appreciate the fact that it allows you to go back and do that, okay? Naturally, right? It's not something you have to struggle for with these type of circuits. That's why I really dig them. I think they're the tops, man. All right. So let's go ahead and figure out our PX, our power across our inductor. This will be 72.9 times 1.4. So I'm taking this value and I'm placing it right here. Okay? And so we'll clear this out. This would be 72.9 times 1.4 equals 102. Okay, I'll just leave that there, VAR. Okay, let me move this up so we have some extra space. Now we're going to do, oops, PR equals, oops, Uh-oh, I think my tiredness is kicking in. I'm starting to make some mistakes here. 95.2 times 1.4. So make sure you guys are checking my work here, all right? 95.2 times 1.4 equals 133.3, and that will be watts. 133.3 watts here. Let's go ahead now and figure out what our power, apparent power, will be. All right. And so again, the formula, again, you could do Pythagorean's theorem here if you want to. I am a man of simplicity. Okay. So I am going to take my 120 volts times 1.4 equals, let's find out, 1.4 times 120. Try that one more time. All right, I got 168 volt amps. Okay, let's compare this. Look, my power, my total power's gone up. Okay, I'm more resistive now too. All right, as you can see by the math calculations here. All right, my phase angle is the next thing that I want to calculate out here. I know what it is going to be, but let's verify it anyway. All right, px over PR, and we'll take the tangent, the inverse tangent of that. All right, let me erase this. Try this one more time, make it a little more clearer for you guys. Okay, so this is going to be 102 over 133.3. Okay, and then we'll take the tangent, the inverse tangent of that. Okay. Yep, I think that tiredness is definitely kicking in. So 102 divided by 133.3 equals inverse tangent. Dead on again. 37.4 as predicted. Okay. Then if we want to get the power factor, okay, go ahead and snap a picture of this if you want it before I erase it. I want to go ahead and calculate out the power factor for this, which is going to equal PR over my total power, or my APP. And again, you can see how many different formulas we have for that here. All of these formulas factor into that. Okay, so we'll come back over to here. So we'll take 133.3 divided by 168. Yeah, 168. Okay, so let's go ahead and do that. 133.3 divided by 168 equals 79. Okay, so my power factor here equals 0.79, which my power factor before equal 0.48. So you can see, as it is more resistive, okay, the relationship between my true power, which is this, and my power total, or my apparent power, my V8, has increased. Whew. Sorry about the mistakes in this one, guys. I was just making sure you were paying attention. I'm a giver. What can I say? All right. So I hope this helped, and I hope this explains how this works. Now, I flew through this one, so if you hadn't watched the previous video, you might be a little lost on this, okay? This is the second step in this one. I have a video that shows this one here where we used the 60 hertz instead of 25 hertz, but now we understand the effects of these. This is going to be important, okay? Very, very important as we continue on in the semester. All right, so I hope you enjoyed the video, and you can now go on to your lab. Feel free to, okay?